All right, okay, so let's just finish up the thermal discussion, giving you an overview of how we calculate these things from quantum chemistry. So the quantum chemical approach to calculating thermal data follows this basic approach. So first you want to calculate the geometry of your molecule. So from different software, which I'll show you, you can calculate the electronic structure or the geometry of your molecule. But molecules are not, they're not static entities, right? So you have a molecule with these different atoms and bonds, and the bonds are always spinning around their axes, right? We call these rotations. Yeah. Okay. Oh, this one we should mute.
Okay, go ahead and speak.
Hello? That's off. Well, this is off too?
All right, so let's
Hello?
just change this.
Okay.
What happens when you're speaking, you're getting this and that, and
Oh, yeah.
I'm getting it really weird.
Sorry. All right, so these molecules, yeah, they're rotating about each of their axes. There's also translational motion as a whole in the molecule. There's molecular vibration, so the bonds are stretching, contracting, vibrating. So each of these results in what we call conformations or conformers, yeah? And so actually all of these conformers exist as you heat up the molecule, especially as temperature increases, you get more rotations, more translations, more vibrations, and they contribute to the energetics of the molecule. So you have to locate all these conformers, and there's software that's available. Basically, the software goes, you draw the molecule in there, and then it rotates all the bonds. It does the vibrations, the translations, and it identifies all the different conformers that are possible. So this is and there's no, this doesn't have to be done at a very high level of theory. Just calculating the geometry of a molecule is pretty straightforward. You could do it at a low level of theory. It's very fast. It's only when you calculate the energies that you have to worry about the accuracy, because that's what determines then the thermodynamic properties. So then you calculate what we call vibrational frequencies. At what are the frequencies at which the vibrations of the bonds are happening, the rotational constants for the vibration, because this determines the moments of inertia, which contribute then to the thermodynamic properties, and then the energy, which is the strength of the different bonds. Then you can calculate the heat of formation using either atomization or isodesmic method. I'll cover those briefly. And then finally, you can calculate from 0 Kelvin data, you can calculate that using statistical thermodynamics. And again, we're not going to talk about statistical mechanics in detail today, but if you've taken these courses, then you know from Boltzmann's equations, you can calculate at higher temperature based on partition functions, the heats of formation at 298, at 300, at 400, the entropy and the heat capacity. So that's all based on partition functions and Boltzmann distributions. And we have codes that are available for that. And then you can compare your results with what's in the literature, either measurement or other quantum chemistry, to see what's accurate. So these are the softwares that are available, Gaussian, VASP. These are quantum codes that are available for quantum chemical calculations to calculate the energetics of a molecule. MolPro. So the ones we use today are mainly Gaussian. That's what's used in combustion community mostly. Some use MolPro. There's another one that's becoming popular. Now I forget the name, but it's used a lot in Europe. But again, there's about 3 or 4. VASP is very good, but typically used by catalysis community because they have more DFT, let's say DFT, density functional theory methods, rather than the very accurate methods that we need for gas phase energy calculations. So when you look at these codes, all of them are trying to approximate the Schrodinger's equation in different ways to get the energy of the molecule. There's different methods. The early ones were called Hartree-Fock methods. And again, within that, you have different methods. Post-Hartree-Fock, or like molar placid perturbation theory, coupled cluster theory. And then you have things like multi-reference methods. Multi-reference methods are the most accurate for getting the energetics of a molecule. And you can see here, roughly in terms of accuracy. Hartree-Fock is very easy and fast for the computation to happen, but the accuracy is poor. As you go to the right, these are, you'll always see these when you read papers about quantum chemistry, different, we call it alphabet soup, okay? So the alphabet soup, you see it, as if the alphabets are longer, typically it's better, yeah, in the alphabet soup, okay? And you see a CCSD coupled cluster with a triple zeta basis set is one of the most accurate, yeah? So, but again, the more to the right that you go, it becomes a lot more expensive. Hartree-Fock, you might calculate the energy of your molecule in like 5 minutes. If you do it a coupled cluster, it might take you 2 weeks, yeah? On a supercomputer, okay, to do this. So now you imagine you want to do a coupled cluster for every single molecule in the world, but everyone, it's impossible. 1,000 molecules, you'll be there forever. And then the guys who own the supercomputer will not be happy with you because you took up too much time. But the multi-reference methods, okay, the leading groups doing this are like in Argonne National Lab, Dr. Stephen Klippenstein, Summit Sandia National Lab, Judith Zador, people who have good access to supercomputers, okay, are doing these things. And also some groups in China now, the multi-reference methods. And you know, if you go to the literature and you want to get very accurate data and you read papers, you know, if they're calculating using Hartree-Fock, the errors are too large for us to even consider it. Once you come to, you know, these types of coupled cluster, yes, they're accurate enough for us, probably plus 1.5 kcal. And multi-reference methods like what they do in Argonne or other groups, you know, you can get up to like less than half a kcal per mole error. Okay, so again, if you're an engineer, you can do these calculations. They just take time, and you need to, again, have access to the facilities. What we do is somewhat similar to what a group in Galway from Henry Curran kind of developed. So M06 is a good functional, again, one of these alphabet soups developed at at the University of Minnesota by Donald Trular, one of the top guys in quantum chemistry globally, probably the top. So he developed this functional, and it's very good for calculating the geometry of the molecule, the dihedrals, the vibrational frequencies, and even the energy. And then you can also calculate using some other method, what we call a composite method, for the energy, 0 Kelvin energy. So you choose your method, that's the first thing. Choose a method that's accurate, but is relatively affordable, yeah, in terms of computational cost. And then you calculate, we calculate the energy of the molecule based on atomization method or isodesmic method. And it's the same as when we talked on the first day about how the thermodynamic properties of a molecule are path independent. It doesn't really matter how you get there, but you can calculate them in different ways. So in the atomization method, say we want to calculate the energy of this molecule, C3H5A. So it's a radical, it's called the allyl radical. There's a double bond here, but it's resonantly stabilized, and then there's a radical in the middle. So this resonantly stabilized radical, if we break it apart into its elements, it's 3 carbons and 5 hydrogens, and the heat of formation of this molecule is the heat of reaction, right? So we have to calculate now, to get the heat of reaction, we calculate then the energetics for carbon, for hydrogen atom, for carbon atom, and then for this allyl radical. That's one way to do it. We call it atomization method. You take your molecule, you break it apart into the elements, and then you calculate for each of those, each side of the reaction, you calculate the energy. And then the other is what we call isodesmic method. Here, instead of doing an atomization reaction, you calculate based on a hypothetical reaction. So I just take my molecule, allyl plus methane. Let's say it reacts to form ethylene plus ethyl radical. And then I calculate the energy for all of these molecules. And then I can get the heat of reaction, and I can correct them for the heat of formation of this unknown molecule based on known values for the other 3. And why would you do this? Well, the isodesmic method is more, let's say, accurate in the sense that because when you do these types of reactions and you calculate the energetics of all the molecules, the quantum chemistry always has errors. It's never exactly right. It might be off by like 1 kcal, 2 kcals. But once, if you do an isodesmic method and you take the difference, those errors in the energy of each molecule will cancel each other out, and you'll get better thermal data. So different people do it different ways. Atomization can be done if you use a higher level of theory. Alternatively, you can go to lower level of theory, but you can cancel out the errors using these types of isodesmic reactions. And here's another example of for a C7H12, an atomization reaction or an isodesmic reaction. What we do, we check both of them and we compare. So let's say for this allyl radical, I take 3 different quantum chemistry methods. I calculate, you can see every method gives me a different energy for the heat of formation using the atomization technique, and also different values in the isodesmic. But the errors are pretty small, right? 42.4 is the average. The max is 42.7. The minimum is 42. So your error is about 0.6 or 0.7 kcal using these 3 methods. However, for this molecule, you can see the differences are quite a bit larger. So anywhere from 12.58 to 15 for atomization. But the isodesmic, the differences are smaller. But in the end, if you take the average, they're still pretty much the same. So what typically people do now is they just use the atomization method, but they choose 3 or 4 different quantum chemistry methods, and then they take the average, they put them together, and they say, okay, now we have good thermochemical data for a molecule. So this is for the molecule, this is for the 0 Kelvin heat of formation. Then we need to worry about the contribution of different conformers. So the conformer distribution just says, based on the Boltzmann distribution, the contribution of each conformer to the energy is sigma, which is the degeneracy, exponential minus delta G over RT, which is the Gibbs free energy, divided by the sum of, again, sigma exponential minus delta G over RT for all the different conformers. So Xi is the contribution for one conformer. So you take one conformer's Gibbs free energy divided by the Gibbs free energy for all the conformers. And again, this is all there in codes. It's available to calculate. All you need to do is provide the conformers Gibbs free energy, which you can get, of course, from the quantum chemistry calculation. And just to show you again, this molecule, hexene, has 14 different conformers of how it could be, the bonds could rotate together. You can calculate all these conformers in codes like Spartan, and then you can calculate their energies. And then you can start to fill a table at different temperatures, because Gibbs free energy changes with temperature, the contribution of each of these 14 conformers to the overall energy of the system. And you can see it changes with temperature. So conformer 1 is more stable at low temperature, whereas other conformers become increasingly important at higher temperatures. So you need to account for this in your calculations when you do these quantum chemistry, and then in the end you can say you can coming up with good thermochemical data. Okay, I think the last is just an exercise. We're not going to do the exercise. But that's it. So that's how we would do it with quantum chemical means. Worry about the conformers, calculate the 0-point energies, and then use the code for the statistical thermodynamics. The challenge, again, is the computational cost. You could do this, but our approach now is let's calculate it for several thousand species. So we have a collaboration with Professor Green at MIT. We calculated for 20,000 different hydrocarbons and radicals that you find in combustion systems, and then just train a machine learning model. And then, of course, 20,000 is not all the molecules that exist, but with 20,000 you can cover most, you could say most different combinations of carbon, hydrogen, oxygen, nitrogen, and then even sulfur. And then you can train a machine learning model to see how molecular structure impacts the thermochemical properties. And I think this approach works well. You can keep building up the database, retraining your models over time. Maybe in a few years, we can have pretty much machine learning models to predict all thermal data fairly accurately. Okay. Now let's move to transport. Okay. So thermal is important for I said the kinetics to get the kinetic data for the reverse reaction, important for the exothermicity or endothermicity of your reactions, the temperature of the system. But all of that is important if you want to do things in homogeneous system, right? So we said shock tubes. Shock tubes are homogeneous batch reactors, rapid compression machines. Even HCCI engine, homogeneous charge compression ignition engine, many people might simulate that as a homogeneous reactor. But anytime we start having gradients in space of mixture fraction and temperature, we have to worry about transport. And when I talk about transport, I'm talking about molecular level transport. So Professor Pitch in the afternoon is probably talking a lot about transport in terms of fluid mechanics, yeah, convection, larger scale transport. But here we're talking about mainly around diffusion, molecular level transport. So indeed, chemical production and destruction, and all chemical reactions are affected by transport. Why? Because we said the rate of a reaction is K, the rate constant, multiplied by the concentration of species, and anything that changes the concentration of species impacts the rate of reaction. And of course, if it's homogeneous, there's nothing other than reactions which affect the concentration. Once you have transport, that's going to change the concentration of the species. Then it'll change the kinetics of the system. So transport can be convection, can be conduction. At a molecular level, the transport we care about is diffusion. Diffusion, which happens at a boundary layer, at an interface, in a flame, for example. So which systems do we care about transport? One is any type of flame, okay? So transport properties play a key role in any type of a laminar premixed flame or diffusion-controlled flame. And let's just see why that's the case. Well, let's say we have a premixed flame. Anybody here do premixed flame experiments? Yeah, what kind of premixed flame is it? Burner stabilized? Yeah. Okay, so burner stabilized premixed flame, yours? The same? So yeah, there's different kinds we see in the combustion community. We'll talk about them tomorrow. But a burner stabilized flame. Another one is I think you might have seen them during the lab tour. We had combustion vessel, right? And Professor Law probably has it here at Princeton. And you have what we call freely propagating premixed flame. So they fill up a vessel with a gas, fuel, and air. They light a spark in the middle, and they look at the flame propagation. And that flame propagation is used to determine the laminar flame speed. So that's a freely propagating premixed flame. We have burner-stabilized premixed flames. We can have counterflow premixed flames, so different types. Let's just look at the case of the burner-stabilized. So this is your burner port. And inside this burner, you're feeding in fuel, air, and this air could be air, it could be some oxidizer, nitrogen, argon, could be different things, yeah? You usually have oxygen mixed with some other inert gas, yeah? Sometimes, usually it's not nitrogen. Many times people use argon, sometimes even helium. It depends on the experiment that you're doing. And this inlet mixture is coming in at a fixed temperature. So Ti, the pressure is fixed typically, and the equivalence ratio, because it's premixed, should be fixed as well. And what you typically see here is, okay, the fuel and oxidizer are coming out of the port. Most of the times this port is looking upwards, okay? It's not sideways, but it's going up. But here I'm just for side, because I'm going to plot it on a graph, so I like to put the burner on the side. And there's a flame here. This is some flame sheet, yeah? And typically what we'll say is, what we'll do is we'll measure concentrations of species, either using laser diagnostics or probe-based techniques, as a function of distance away from this burner port. So this burner is here 0, and we say this is some distance x. So sometimes people say distance away from the burner or height above the burner, HAB. are common ways. And your graph would then look like this. So you can look at the concentrations of species as a function of distance or height above the burner, HAB. So what is it going to look like? You're going to have some curve that looks like this. That's the fuel, okay? So this might be the fuel profile. It'll look something like that. The fuel will be coming out of the burner. As it enters, as it's entering into the flame region, it'll start to be consumed. Eventually all the fuel is consumed. Then you'll have something like this. This is probably CO2, okay? A product species that's formed after the flame. Let's have a different color here. Then you have some curves that look like this. This is some intermediate species. Could be, let's say the fuel was C2H6, okay? Ethane is the fuel. You could have some intermediate species, probably something like formaldehyde might look like this. CH2O, formaldehyde. So it's produced as the fuel is being consumed, but then as it enters into the flame, it's also being consumed, oxidized fully to make something like CO2. And then you might have also then the temperature. This could be a temperature profile. And what this thing says is, okay, this position here, where everything happens, is your flame. This is basically your flame region. So you can think of your flame as your high temperature reactor. Maybe it's around 1800, 2000 degrees Kelvin. So what do you see here? You have first of all, we have a gradient in temperature. On one side of the flame, it's cold. The other side of the flame, it's hot. The flame is very hot. Then as this gradient in temperature is, of course, going to change the kinetics. Yeah, because K is dependent on T. In addition, you have a species like fuel, intermediates like acetaldehyde, which as they enter the flame region, they are having gradients in their concentration, and that gradient in concentration is of course going to change the kinetics of the system. And of course, the transport which is governing this system is mainly convective coming out of the burner, right? So, and then you have a premixed mixture, you light up the flame is trying to come back and consume all this stuff. We call this a burner stabilized flame because the convection of the fuel coming out of the port is pushing the flame away, but the flame wants to come back. So eventually it becomes balanced depending on the flow rate. If your flow is too low, the flame will just come and sit on the burner. If the flow is too high, the flame will blow away. Yeah, so they try to balance out this flow to get the flame to stabilize some distance away from the burner. And then, but at this point where the flame is stabilized, everything governing within the flame sheet, the transport is from diffusion, okay? Diffusive processes. And that diffusion is governed by molecular transport, not bulk transport. It's a molecular transport. So we need to know then how do different molecules diffuse together depending on the gaseous environment that's there. And for this, we need molecular transport, things like determine the diffusion coefficients, the viscous flow, the viscosities, the thermal conductivities, as well as thermal diffusion, because this will determine the temperature in that region. And thermal conductivity affects thermal diffusion coefficient. So these are the different types of experiments. Again, you might be doing experiments and you look in the literature and nobody has a kinetic model with transport data because not many people work on these types of flames. So pre-mixed flames, other kinds of one-dimensional flames like counterflow diffusion flames. The bottom one here is a counterflow diffusion flame. Anybody work in counterflow? Yeah, a few of you are working in counterflow system. Of course, transport is important in that system. Two-dimensional flame, laminar flame, not turbulent. So this is like your typical candle flame. So the fuel's coming from the inside, the oxidizer is on the outside, and it's laminar, so you form a laminar diffusion layer where the fuel and oxidizer mix. Some people sample the species inside of these flames. Oftentimes, this is used to study soot formation processes. You could also have inverse diffusion flame. The oxidizer comes from the inside, and the fuel comes from the outside. Again, it's just a different configuration of the same type of cold flow configuration. This is a 2D system, okay? The counterflow is one-dimensional because you have gradients only along this, let's say, y-axis. But a cold flow flame is two-dimensional because you have gradient along this axis, z, but then also along r, along the radius. So a bit more complicated to simulate, but still you can use these types of flames for model validation, kinetic model validation, okay? Let's look a bit more at this counterflow flame. So counterflow flame is, again, two burners facing each other. It's basically two of those burner ports. And here you have fuel, and here you have oxygen, or oxidizer, okay? It could be air, it could be a mixture of oxygen and nitrogen. And the key feature of a counterflow diffusion flame is that you form a stagnation plane here, stagnation plane. This is what we call stagnation point. And this happens because the momentum of these two streams is balanced. You form a stagnation plane, and then you might ignite a flame which sits here. The flame could sit either side of the stagnation point, depending on the stoichiometry. And what happens here is because this is a stagnation region, all the mixing between the fuel and the oxidizer only happens because of diffusion, because it's kind of like a boundary layer, the stagnation plane, and the mixing is due to diffusion only. And this is kind of what the structure of these flames look like. So this is, again, distance between, so 0.8 here is probably on the fuel side, 1.6 is on the oxidizer side, and as you move between the two ports, there's a high temperature, sorry, this is showing the stagnation, the velocity in the dashed line. So the velocity crosses 0 here, somewhere between the two burner ports. So that's the point at where the stagnation plane exists. Actually, this flame seems to be sitting on the fuel side, so the highest temperature is on this side of the stagnation plane. And then you start to see how the profiles of species look here. So this is the oxidizer. Oxidizer is on the right side. It comes and it's consumed in the flame, and then it becomes 0. The fuel, in this case, is butanol. It's coming out the burner port, and it's consumed in the flame. And these are the intermediate species. And again, the main thing here is that in this region of the flame, you only have, in the stagnation plane, diffusion processes are governing the mixing of the fuel and the oxidizer, which then impact all the kinetics. So if you want to determine or validate your kinetic model against these types of flames, of course, you need to still have accurate thermal, accurate kinetic parameters, but then you also need accurate transport data. And we'll look at why, what errors in transport data might result in your calculations. Okay, so yeah, this transport is used, again, as I said, for diffusion, for viscosity, for thermal conductivity, for thermal diffusion. All of the basis that we have for transport in kinetic model validation is based on gas kinetic theory, and it tries to relate the macroscopic properties of the gases, like the temperature, the pressure, the thermal conductivity, the diffusion, to the microscopic quantities, which are associated with the mass of the molecules, the velocities, their energies, their internal degrees of freedom, so all the molecular level features of molecules. So similar to thermal, how we could use thermal could be based on the molecular structure of molecules. Also, the transport properties can be calculated from the molecular structure of the properties. So we find a way to get the macroscopic properties, like diffusion, related to the microscopic properties, which are the molecular level properties. And this was all based on gas kinetic theory by Maxwell, Boltzmann in the 1800s. And those theories were then parameterized to connect macroscopic behavior with microscopic behavior based on this certain equations by Chapman and Enskog in the mid-1900s. So they showed how you can use molecular properties to calculate transport data, specifically diffusion coefficients, viscosity, and other things based on some assumption that molecules are behaving as symmetrical particles. And this is based on something called Lennard-Jones theory, okay, Lennard-Jones potentials. The concept is pretty straightforward, okay, in gas kinetic theory. It's a simple model which tries to say that if you have two molecules or two atoms, how does the energy of the system change as these two molecules either come close to each other or move away from each other? And in diffusion, that's all that's happening is molecules are moving together. The rate of diffusion only depends on the attractive and repulsive forces between the molecules. So this is a potential energy diagram. As you take just a representation, potential energy on the y-axis. Let me get the laser. And distance between the atoms or molecules on the x-axis. So as two molecules are far apart, okay, there's not much potential energy in the system. There's no real interaction between the molecules. As these two molecules start to come closer and closer and closer together, initially there's an attractive force which starts to pull these molecules together. Eventually you reach the minimum potential energy where the two molecules are at the optimal distance from each other because of their attractive forces. But then if you bring them too close together, they'll start repelling each other. We call this the Pauli repulsion. And then the potential energy increases because the molecules are too close together. And the entire assumption in Lennard-Jones-based gas kinetic theory is that this diagram can be related to some simple understanding that these molecules are essentially spheres. Spheres which have attractive and repulsive forces. And then these forces are going to be dependent on the size of the sphere and some other, say, molecular level properties of these spheres. So the potential energy is simply then the difference between the attractive forces and the repulsive forces. And then this is VLJ is the potential energy based on the Lennard-Jones potential based on the distance between the molecules is A, some parameter A, okay, divided by R to the 12, R being the distance between the two molecules, minus B over R6. So again, and this B over R6 represents the attractive force, and then A over R12 represents the repulsive forces. The minimum in this energy system is what we call eta, the potential well depth of the system. Sorry, I'm sorry, my Greek is bad. Is it epsilon or eta? I think we say epsilon for this one, right? Yes, okay. And this is a potential well depth, and then sigma is a collision diameter, yeah? So this is the collision diameter, this is the potential well depth. So with these two parameters, we can determine the potential energy of the system. And then we go on further, and in transport and combustion simulations, we take this basic theory and we use it to determine things like viscosity, binary diffusion coefficients. I won't go into all the details of this. I just want you to see in these equations what are the molecular level properties that matter. So one is the mass of the molecules, mk. Kb is a constant, Boltzmann constant, temperature. Okay, sigma is the collision diameter. Collision diameter is a function of the molecular structure, and we'll show how we can get that. And then something we call a collision integral. Collision integral in this case is sigma 22 star. This sigma 22 star is based on the reduced temperature, which is a function of epsilon, which was at potential well depth. So now we have two parameters, sigma and epsilon, to get the overall viscosity. You can see this epsilon is convoluted inside of this collision integral, which we have to look up inside of a table. Okay, and then you can also use this to get the dipole moments. So the dipole moment is also based on epsilon and sigma, and then we have to use some type of tables to look up the collision integral sigma 22 star, and there's a reference I'll show you later on we use to get that. Okay, now, and then the same thing for diffusion. So that's for viscosity. Again, it's based on mass, reduced mass of the system, and then also on the sigma and the collision integral. Similarly, for binary diffusion coefficients, we follow this what we call Chapman-Enskog kinetic approach. Here again, the binary diffusion coefficient is a function of the reduced mass of the system, which is the reduced mass between two components that are diffusing together. N is number density. So then sigma 1, 2 is the collision diameter between the two species squared, and then another collision integral, sigma 1, 1 star. And there's more equations. You guys can look at these things. If we write them in terms of pressure now instead of number density, it looks like this. And again, the main thing is we need to determine the mass of the binary partners, the mass of the molecules. Epsilon is used to determine the collision integral, and sigma jk, which is your collision diameter. And we look up these collision integrals in tables. These tables are available. This is a book from the 1960s, The Transport Properties of Gases by Monchik and Mason. They basically tabulate all these different collision integrals based on differences in potential well depth. So you have T star, you have dipole moments, and then you can calculate potential well depth, and you can calculate this ratio of dipole moment over T star, and you can get these different collision integral values. And in Chemkin and Cantera, all they're doing is they have these tables built in, and they're looking up, based on the transport properties you provide, they'll look up the collision integral, and then they'll use that to calculate the diffusion, the viscosity, the thermoconductivity. So this is for polar gases. There's one set of tables, and that's why you'll see when you write your transport data in the file, you have to define, is it a polar molecule or a non-polar molecule, based on the dipole moment. So this is one table for polar, and this is another table from Hirschfeld and spots for non-polar gases. And again, these tables are all built into Chemkin and into Cantera today. So what do you care about? We care about how do we calculate those important parameters, which then go into the diffusion equation and viscosity equation. And those parameters are the Lennard-Jones potential well depth, epsilon over Kb. This should be a Boltzmann constant subscript. Okay. In Kelvin, we need the Lennard-Jones collision diameter. In angstroms, we need the dipole moment, because that's used to determine the polarity of the molecule and which table to look up in. Then you need the polarizability in cubic angstroms and the rotational relaxation number Z rho. So if you look at a transport file for Chemkin or Cantera, it's these 5 numbers, okay? And in order. Potential well depth, collision diameter, dipole moment, polarizability, and rotational relaxation number. This has to be provided for every species in your model. Radicals, neutral species, and so on. So how do you get these? Well, again, we have good equations at hand. You can look at these equations anytime you like. The collision diameter, we can base it on the critical pressure and critical temperature, and then some constants. These constants have been fitted previously in a paper by Hawley in 2009, which draws from previous work from T, Goteau, and Stewart. Essentially, they're saying that you can determine the sigma only knowing the critical pressure, critical temperature, and boiling point for any molecule. And these things are easy to look up. Critical pressure, critical temperature, boiling point. You can look them up in NIST, webbooks, many databases available. From that, you have this equation, which you need to use to calculate then both sigma and epsilon. And once you have sigma and epsilon, your code will use that to calculate the binary diffusion coefficients and so on. Yeah, I don't need to tell you too much about these equations. They're pretty straightforward. And again, they're simply just fitting functions of how epsilon and sigma depend on things like critical pressure, temperature, and boiling point, which are molecular features. These are things that are properties of molecules that you can look up. For example, this is the NIST chemistry webbook for any molecule, like, say, for example, 4-methylheptane, you can go and look up the boiling point, the critical pressures, critical temperatures, and they've compiled these, and the uncertainties are pretty low. I mean, they know these things within a few Kelvin with a good level of accuracy. There'll be some molecules that you won't find this data for, like very long-chain hydrocarbons. So it's, in order to do that, you can develop a very simple fitting function. So you can see here, these things, this is a critical temperature and critical pressure as a function of carbon number. And you can see here, they're pretty straight lines, or lines that can be fit with a simple function. So the critical temperature, critical pressure, shown here, for example, Tc is the critical temperature. I believe this is for different fatty acid metal esters. So for molecules that look like this, this is called a fatty acid metal ester, okay? So there'll be some, and these are commonly found in biodiesel. So these things, you won't readily find them in NIST, but, and this one is for 4 carbon atoms. The biodiesel fatty acid metal esters have 15 to 20 carbon atoms, so you can just simply extrapolate the critical temperature, critical pressure. You can collect data for molecules that look the same, and because it's only really a function of mass for a family of molecules, then you just extrapolate to higher masses. Now, does all of this matter? That's the thing we care about. Yeah? Do you need to, okay, again, you'll find some people that just put dummy values for transport data. They say it doesn't matter. Transport is transport. Who cares? The flame speed is not dependent on transport that much. It's somewhat true. The flame speed is mainly dependent on the transport of hydrogen, oxygen, OH radical, O radical, the radicals, because that's what exists in the flame. The fuel is far away from the flame. So who cares about the fuel and all the intermediates? Just get the transport right for the small species. And that's what many people do, and they put dummy numbers for everything else just to get the code to run. Okay, but it depends on the type of system that you're running. So this is an example from, I guess Smallbone was here in Princeton, yeah? Looking at the effect of Lennard-Jones parameters on the left side, the effect of the binary diffusion coefficient on, I think this is for flame extinction phenomena. So again, this was an experiment in a counterflow diffusion flame. The fuel was N-heptane. So N-heptane was coming from this side, the oxidizer is coming from this side, and actually they're looking at something called flame extinction, which is very important in aircrafts for like high altitude extinction phenomena. And typically those flames are non-premixed flames at high altitude, which may extinguish. So they will be, the canonical experiment is a counterflow experiment where they keep increasing the flow rates of the two streams, and based on the strain rate, the amount of convective strain that's there on this flame sheet, eventually it'll extinguish, and they measure that extinguished strain rate, extinction strain rate. And that's an important property of a fuel which is used in the design of gas turbines, mainly because of high altitude extinction phenomena. So they show here, if you have the diffusion, the binary diffusion coefficient, which is a function of, as we said, MJK, the reduced mass, sigma, and the collision integral, then you will have an error, a significant error in the extinction strain rate. So if you get the fuel diffusivity wrong, the oxidizer diffusivity wrong, the nitrogen diffusivity wrong, in their respective binary gas, so nitrogen and heptane, oxygen and heptane, then you're going to have a huge sensitivity on your extinction strain rate. Whereas all these small molecules, and these are the reactions, for example, they're showing here H plus O2 going to O plus OH, the most important reaction in kinetics for flames and flame stability, has no effect on the extinction strain rate in comparison to the transport properties. So you got to be relatively right in getting at least the fuel, the oxidizer, the nitrogen well. Now you might ask, okay, what about all those intermediate species? Well, their study shows that the intermediate transport doesn't really matter for extinction, okay? But if you're trying to trying to do something like a sampling of a flame with a probe, and you're trying to measure species concentrations. For example, species concentrations here. The species concentration of formaldehyde will be sensitive to the binary diffusion coefficients of formaldehyde inside of your system. Again, so it depends on what you're trying to predict. Here on the right is ignition. Again, counterflow ignition, so this is for high altitude relight. Again, in a canonical experiment, they took two streams together, they take away the flame, and they just heat them up, heat up the streams as they're flowing together at a fixed strain rate, and measure the ignition point. And that's used to represent high altitude relight in a gas turbine. So here at different strain rates, different velocities of those two streams, what is the ignition temperature? And this is showing if you just change the collision diameter by 25%, your predictions can change by almost 100 Kelvin. So, and why collision diameter matters? Well, because it's in the denominator squared for the binary diffusion coefficient, so it has a big impact on the eventual ignition process, which is driven by diffusion of fuel and oxygen. Okay, so those are these are the most important things. If anything you're going to get right in your transport file, try to get the fuel, the oxidizer, the nitrogen, maybe some of the major intermediates, and try to get sigma correct, the collision diameter, as well as the potential wall depth. Now the rest of the stuff in your transport file, so the dipole moment, the polarizability, the rotational relaxation moment, they have very little effect in the end on the overall diffusion and viscosity calculations in the end. So I'll show you how we do them. So the dipole moment, okay, there's no simple way to calculate this. It's very much dependent on the electronic structure. You either calculate it from first principles or you're looking it up in a table. So this is a book by McClellan, very old book, 1963. You probably have to go to the basement of your library to find this, or maybe if your library is lucky enough to have digitized it, you might have access to it. But they have dipole moment of pretty much every molecule you can think of. And okay, if your molecule is not there, you can find something that's pretty much similar and approximate it. It's not going to make a big deal in your transport properties. Polarizability, this is related again to the electronic structure and the electronic cloud. Simple equation can be used. This is an equation that fits fairly well for anything with carbon, hydrogen, oxygen. You can use this equation to get the polarizability. Now, some of you might be doing ion plasmas. The transport is important in plasmas for ionic species. Now, there you're not going to use this simple equation for polarizability, because once you have a charged molecule, you're going to want to know your transport properties fairly well for those charged molecules. And there's other databases. Typically, UMIST database can be used for transport for ionic species. This is some stuff about how people measure binary diffusion coefficients. I will pass over it. And I'm going to talk more than what is the impact of all this, okay? Let's skip to this. Okay, these are some nice papers that were recent, okay? So I think we should understand what is the impact of all this stuff. So slide 23. So these are two papers from University of Michigan about 15 years ago. Around 15 years ago was only when people started to think about transport. Professor Hai Wang, who's now in Stanford, Professor Law, Professor Violi, they started to try to understand, okay, do we really care about transport? How accurate do we need to actually get it or not get it to get very important things like extinction in gas turbines or reignition in gas turbines accurate? For flame speed, the main transport that matters is the small molecules, H, OH, maybe oxygen, hydrogen. The fuel transport doesn't even impact something like a premixed laminar burning velocity. But again, it's mainly these diffusion-controlled ignition, extinction environments which are important. So, what is the effect? There's these two nice papers, both from Professor Violi at Michigan. The effect of molecular configuration on the binary diffusion coefficients of linear alkanes. and also the mutual diffusion coefficients of heptane isomers in nitrogen using molecular dynamics. And what these papers were trying to do, because all of the stuff we're using in combustion, these are approximations. All this gas kinetic theory, Leonard-Jones potentials, it's all approximations. It's not really how diffusion happens, but these are, the Leonard-Jones potential diagram is just an approximation of how the potential energies of the system changes. So they're trying to understand, how to, do we need to improve this or is it good enough? Yeah. And how you do that is, in kinetics and thermodynamics, we use quantum chemistry. Well, in transport, we have to use molecular dynamics. So molecular dynamic simulations, again, from first principles, try to understand what are the diffusion processes. So again, you can do a molecular dynamic simulation, and from first principles, you can look at the attractive forces, the repulsive forces, you can calculate the diffusion rates, and then you can compare to all these simpler engineering approximations that we're making actually fit well with the molecular dynamics data. Now this Leonard-Jones theory, yeah, it assumes two molecules are spheres, yeah, and this has some collision diameter. Big molecules will diffuse slower than small molecules because the collision diameter is bigger. But around 15 years ago, Professors Haiwang, Edlaw, Violi, they said, but real molecules are not really spheres, yeah? Like hydrocarbons, gasoline molecules, like alkanes, long-chain alkanes, they're not spheres, they're more like long, linear hydrocarbons, yeah? Small molecules like hydrogen, oxygen, nitrogen, yeah, they're pretty small spheres. They might behave like following Leonard-Jones theory, but what about the large hydrocarbons, now that we're interested in like jet fuels, diesel fuels, and so on? So she did a study to look at linear alkanes and to see if these approximations are still valid. And this is just showing here at different temperatures, she can calculate the binary diffusion coefficients for different molecules, okay? And you see here, the first plot is for ethane, a relatively small molecule, C2H6. And you see here the molecular dynamics and the Chapman-Ensog theory, which is what we're using, all based on Leonard-Jones gas kinetic theory, is very accurate. Yeah, the Chapman-Ensog fits fairly well with the molecular dynamics. You go to even to C6H14 and hexane, now 6 carbon atoms. Now you start to see slight deviations, but the deviations start only appearing like about high temperatures, 900, 1000 Kelvin, yeah. Then you see here C12H26. So this is dodecane. This is hexadecane. Dodecane, very common molecule for kerosene or jet fuel. Hexadecane for diesel fuel. You start to see, okay, the deviations become quite large, yeah. So here at 900, 1000 Kelvin, the diffusion coefficients might be about, might be off by about 10 to 15%. And then you ask yourself, yeah, does this matter or not, okay? She's just showing the Chapman-Ensog theory worked well when combustion community was interested in small molecules. Now you're getting interested in larger molecules. The Chapman-Ensog theory doesn't seem to be as accurate, yeah? And now you can also look at different isomers. And again, these are different isomers of heptane. The diffusion coefficients are shown here. So N-heptane is the first isomer. Then you have things like 2-methylhexane, dimethyl alkanes. And you start to see even as you introduce branching in your molecule, you have differences in your transport data. Now, typical Chapman-Ensog theory, Leonard-Jones, it assumes molecules are spheres only based on the molecular mass. So things like branching are not really accounted for in that theory, yeah? So you start to see here, they can have some changes. And even now she shows that at 1000 Kelvin, the differences are even larger. Okay, and again, we asked our question, does all of this matter? Well, if you want to get things more accurate, you got to change your entire code, yeah? Because all of ChemKit is based on Chapman-Ensog. And How do you change? Then you have to go and reformulate the entire code, make new lookup tables based on molecular dynamics. Well, nobody wanted to do that. So we still use Chapman-Enskog. Nobody in the community has yet moved away from it. One of the reasons is, again, if you look at these differences, they only manifest themselves at high temperature. Yeah, like most of the differences are above 800, 900, 1000 Kelvin. Well, the fuel rarely survives all the way to that temperature, right? By the time you get to like 900 Kelvin, and we'll see that in kinetics, right? And when we look at the reaction mechanisms, most of your fuel's gone. It's already been reacted to intermediates, yeah? And then those intermediates are things like formaldehyde, acetaldehyde, ethane, methane, small hydrocarbons, radicals, which behave pretty much like small spheres. Yeah, so your fuel never really sees the very complicated high temperature environment. It's diffusing mainly when the temperature is low and mixing. Then as it reaches like 600 Kelvin, it's already starting to react. By the time it reaches these temperatures where you see these differences, 900 Kelvin, 1000, the fuel's pretty much gone. Yeah? It's already broken down to its intermediates. And these are the approximations you try to make and rationalize them. Okay, we should finish in the last hour. Let me take a break, and then, because the rest is, standard stuff. We're going to now consider this chapter closed, and we're going to start looking at the kinetic models. Okay, so take a break.